Hello, this video is a review of section 14.1, basic definitions in vectors in 3D. Most of this section is just an extension of what we know from vectors 2D. Now we have three axes, x, y, and z. They are perpendicular to each other, and when we need to figure out how they point, we use the right hand rule as we have here in the picture. Well, you know how this works. So we represent vectors with arrows. The arrows could be having any starting and ending point. For instance, this green over here has a starting point at A and has ending or terminal point at B. If we take the same vector and we translate it so that the initial point is at the origin, then we say that the vector is in standard position. Standard position. In that case, if the terminal point is a point P with coordinates x, y, z, we can write the coordinates of the vector v as being those coordinates x, y, z exactly. We may want to find the magnitude of the vector v, the length of the arrow that represents the vector, and to do that, this is an extension of Pythagoras. We need to take the sum of the squares of the coordinates and then compute the square root of this. Excuse me. All four vectors in the picture over here, the orange one, the green one, the sky blue one, and the purple, are actually equal because they have the same magnitude and direction. We wish to perform operations with vectors. So over here we have two ways of looking at the sum between the vector u and the vector v. So here we are doing the sum of u plus v. We can think about this with a triangle, thinking that we are starting the vector v where u ends, and then the vector u plus v is going to go from the initial point of u to the terminal point of v. Or we can use the parallelogram rule. So we have vector u and v starting at the same point. We complete the parallelogram that they form, and then we take the diagonal going from the initial point of u and v to the other end of the parallelogram, and that's the sum. Those two methods are of course equivalent, but it will be convenient, I believe, remember the parallelogram, since the other diagonal over here that I drew with black, this represents the vector u minus v, and it could be worth remembering that. In coordinate form, let's say that our vector u is given by the coordinates x, y, z, while our vector v is given by coordinates a, b, c. When we find the vector sum between u and v, we get a new vector that has the first coordinate, the sum of the first coordinate, x plus a, the second coordinate, the sum of the second coordinates, y plus b, the third coordinate, z plus c, the sum of the third coordinates. So everything works as we will expect that the sum has to work, and the usual properties that we know from sum of real numbers, they also apply. For instance, u plus v is the same as v plus u, so it doesn't matter the order we are summing. There are more properties, and you should check them in the book. This is just a review. I'm not going over everything that you are supposed to know. The next operation with vectors that we wish to do is the multiplication by a scalar. In this case, we are going to take a number k in the real numbers, and a vector v as here, and we are going to construct a new vector k times v. How is this new vector defined? Well, depends on whether k is greater than 0 or not, but in any case, if we take the absolute value of k and we multiply it by the magnitude of v, this is the magnitude of the new vector. So depending on the k being greater or less than 0, we need to change the sign or not. And then for the direction, k, v will have the same direction of v if k is positive. That's the example on green over here at the left. And it will have the opposite direction. So the direction of minus the vector v when k is negative, as we have in the orange vector over here. In coordinate form, when we have the vector u given by x, y, z, as before, and we multiply by k, the new vector is going to have coordinates that are the same as the old one multiplied by the real number k. Yes. One more thing that will be worth remembering is that I'm running out of space over here. Two vectors are parallel, so let's say u is parallel to v. If and only if we can write one vector as a multiple of the other, so we can write u as kv for some k in the real numbers. Let me somehow separate this from the rest. Just run out of space slightly. So this is a necessary and sufficient condition for two vectors to be parallel. One more thing I would like to remind you about this is that sometimes when we have a vector that is not in standard position, vector A going from a point A to a point B, we can write it as a difference between two vectors that are actually in standard position. So in a picture, this will be like this. Let's say we have the vector AB. Yeah, so going from the point A to the point B, and let's say the origin is a point here 0. So here we can consider the vector going from the origin to A. Okay, that's not really going from the origin. I need to move it a little bit. No problem. There you go. And we also have the vector going from the origin to B. I also need to fix this one a little bit over here. And we can see that this is the difference between the vector OB and OA in the way that we look at the difference as the non-main diagonal of the parallelogram of the vectors OA and OB. So that will be useful to remember. We need to remember also about unit vectors. In 3D, the unit vectors that go along the axis are I, j, and k. Well, those are the unit vectors we use a lot, not the only ones, of course. There are infinitely many unit vectors. Any vector with length 1 is a unit vector. But if we have any vector u with coordinates x, y, z, we can write the vector u as, sorry, I moved things a little bit here, x multiplying the unit vector in the direction of x, I, plus y multiplying the unit vector on the direction of y axis, the vector j, plus z times the vector in the direction of k. If we have any vector over here, I don't know, let's say a vector v, we wish to find a vector in the direction of v, but we want that vector to have magnitude 1, then what we need to do is to consider the vector v divided by the magnitude of the vector v. So this vector has direction of v, but it's a unit vector. If we try to find the magnitude of this new vector, this is equal to 1.